Okay, so today we'll be talking about quantum mechanics, and we will talk about we will talk about Heisenberg uncertainty principle. Uncertainty principle. Okay, so if we talk about classical physics, in classical physics, when we want to do measurements. Okay, so when we want to do measurements, that measurement could be anything: speed, distance, or time. I'm just taking a basic example. This distance over here could be the vertical distance. Vertical distance, okay? Now, when we do this measurement, we what value we get is a fixed value. Fixed value, okay? That if it's falling down till here, the distance is covered is fixed, exact value. Okay, so when in classical physics there's nothing known as probabilistic measurement. It doesn't exist in classical physics. Okay, so every measurement every measurement gives a a certain value. Okay, so then um, one more example could be this: that a car or a truck is moving in this direction and it hits a certain car. Okay, now the change in momentum will will be will be a certain value. You won't see anyone saying, no one will say in classical physics that the momentum of this momentum of this system is momentum of this system is in between a certain range. Okay, I'm putting infinity here so that uh, I'm talking about everything, like the range between positive infinity to negative infinity, so I don't have to fix put a certain guessing value, as this covers all the values. You will it This is wrong. It doesn't happen in, whoa, big one, sorry, doesn't happen in CP. Okay, classical physics. Now, but if we talk about the same scenario, but now we will include a quantum system. Okay, a quantum system or quantum physics. Okay, when we include quantum physics, quantum mechanics, in quantum mechanics, if it's better if I write quantum mechanics here, it makes it more interesting wording. Mechanics. Okay, now as we know, in quantum mechanics, in quantum mechanics, in quantum mechanics, we talk about particles. Okay, so we have a particle. Let's suppose particle 1, and it moves. Let's suppose in x direction. Okay, what you will be noticing here, the difference you will be noticing here is with as respect to classical physics, um, the position the position is now probabilistic, as well as the momentum is also probabilistic, is also probabilistic. So meaning, and they both combine to make this equation. Now what is this equation? This equation is Heisenberg's uncertainty principle. Uncertainty principle equation. Equation. Now, what does this equation tell us? It tells us that even though at quantum level measurements can be done, measurements can be done, but there's a downfall. Measurements, when measurements are done, when measurements are done, uh, it affects the system. It affects the system. Okay, what do I mean? For giving the such as we if I give an example, let's suppose if we measure if we measure light in in horizontal direction, okay, and then um, vertical polarizer is used. Polarizer, sorry, not fire, polarizer. Okay, polarizer. Okay, Okay, so what happened actually is, at first we were measuring horizontal, measurement was made, but on measurement. Let's suppose the second is a the one we did here is a measurement. So now the vertical direction the current is a current change. Okay, so then when we come back to our equation when we come back to our equation this equation over here, this is the equation shows uncertainty between the two, shows uncertainty. Wait, did I write uncertainty or no? I did. Uncertainty principle shows uncertainty between between x and y. Okay. Mm, and it's vice versa. if if one measurement is made if one is made, let's suppose x, then p will decrease. Okay, let's suppose if it's measured in terms of um, I would say the arrows over here are showing increasing accuracy, decreasing accuracy. Okay, so and this sign over here is Planck's constant. Okay, Planck's constant. The value of this was I don't remember. Sorry. So yeah, but just know that it's a constant. Okay. So there's this common misunderstanding that uncertainty principle, uh, makes us know about more about the preciseness of one measurement, completely finishes the preciseness or the information about the other quantity. But that's fully wrong. The information of unmeasured quantity doesn't fully vanish. Okay, so what by the way, this symbol over here represents the operator. Okay, and when, okay, yeah, one more thing. When when it's unmeasured, wave function is part of quantum mechanics. It will be everywhere in quantum mechanics. You cannot skip wave function. So wave function is is there, is always there, it will be there. Okay, wave function cannot be reduced. Okay, but wave function collapse. What does wave function collapse does is it causes the, what does it do? It we are we are forced to turn into classical system. Classical system. Okay, so, and then it brings us to a very like good point. uh, these two combined makes us an uncertainty equation. But look at this: the moment one measurement is made, sorry, I'm just struggling, made, what happens is QS, quantum system, quantum system to classical system. Okay, uh by the way, this whole the this multiple particles p1 p, it's the same particle but it's in different particles. I made different particles because what I wanted to show was that if, let's suppose, we measure its momentum, then these are the possibilities in which the particle could be. As now, what actually happened was that the probability of knowing the x, or the direction, or the, sorry, position, actually x's position, was decreased in preciseness. That the value we could have attained from measurement reduced. Okay, and again, even the values we attain from these equation, x and these values attained are probabilistic values. Probabilistic values. Okay, so, okay, there was a specific equation in terms of wave function that represents the width of the wave function. Okay, so the equation was but to be, I mean, more when we talk about uncertainty principle, the wave function is representing how well we know about the position and the momentum. Okay, so the equation which we were supposed to, the wave function equation for x and p is uh, so it's in terms of integration, and they are written in form of, yeah, this is what it is actually. Let me make space. For change in x, it's x integration of sorry, norm square or the absolute square of wave function, first equation, and the second equation is same, but this time we will use a phi. Okay, instead of using psi function, we'll use phi function in terms of momentum, of course. Expected value of p would be square of momentum here as well, square. Same we have over here as well. If we want the expected value, we square the position as well, square. Okay, sorry, in terms of momentum. So this is in terms of position, and this in terms of momentum. And again they combine these two. By the way, delta over here is this is delta represents the frequent 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 changes. Yeah, so that's it. Thank you.